Hello there, Mr. Sutton here, bringing you this first in a series of 4 lessons on the FTC, the Fundamental Theorem of Calculus. In this one, we'll be using the FTC to take derivatives of integrals. For your warm-up on this one, pause the video and try the following 3 problems here. The last one's a fill-in-the-blank for you. All right, let's see how that came out. So for the first one, antiderivative of 3x squared, we can use our reverse power rule. Exponent becomes a 3. Dividing by that new exponent, the 3's cancel, so this is just x cubed plus c. Next, we're taking the derivative of what we just did in part A. So this is really just the derivative of x cubed plus c, which is just going to be going term by term using our power rule, 3x squared, and then that c becomes a 0. Well, look at that. We took the derivative of an antiderivative, and we got what was inside the integral. What does this mean about derivatives and integrals? Why, if one undoes another, then they must be inverses. What we've just discovered on that last warm-up is basically the first part of the Fundamental Theorem of Calculus. To state it officially, let's say that big F of x is the integral from some constant a to some variable x of some function f of t dt. If that function f is continuous on the interval from a to b, then the following is true. So f prime of x, which is to say the derivative of all this stuff here, is going to be equal to just f of x. So that's kind of like on our warm-up where the derivative and the integral cancel each other out. But this is a little bit different than the warm-up because we now have something that's kind of like a definite integral. I mean, we have a variable as one of our limits of integration, but we do have this constant lower limit of integration. So to kind of state this in plain English, the derivative of an integral that has x as an upper limit, like we do here, is just going to be the integrand, f in this case, with the x plugged in. Let's go ahead and give the FTC a test drive here. Pause the video and see if you can find the derivatives of the following 3 integrals. All right, let's start with part A. So again, if you have x as an upper limit and you're taking the derivative of this whole thing, you're essentially just taking the integrand with x plugged in for whatever dummy variable was in there to begin with. So in this case, f prime is just going to be 3x cubed minus 5x squared plus 7. That is it. Nothing else. All right, let's look at part B. Same deal over here, but now we're going to have 8x to the 3/5. And then finally for part C, this is going to be negative 5e to the 3x. Seems pretty easy, right? Almost too easy. So at this point, we're going to take a look at a more general case of the fundamental theorem. In this one, we have a variable in the upper limit, but it's inside of another function. So if we're just starting our normal reasoning here, we could say that the derivative of this thing is f of whatever our variable up here is, so g of x. There's just one problem, though. We just took a derivative of something with an inner function. What are we supposed to use when we take derivatives of things with inner functions? Oh yeah, the chain rule. So if you're dealing with more than just x, you're going to need to use the chain rule on whatever that upper limit is. So in this case, we would have to multiply by the tail, which would be whatever g prime of x is. Now you might wonder, well, why didn't we just do this before? Why is there a different rule when we have a function up here versus just x? Well, if you think about it, x really is a function. You could technically do this with x also, but what's the derivative of x? Well, it's just a tail of 1. So there wouldn't really be any point in writing that tail, but if you have something other than just x here, you're going to have a tail that looks like something other than just a 1. So let's do an example now where we have a derivative we're trying to take where our upper limit is something other than x. Pause the video and see how far you can get on this one. All right, so using what we said before, we need to do f of g. So that means we're going to need to do x squared squared, basically replacing all of these with x squared, plus 5 times x squared minus 10. And now we have to multiply by the tail, which is the derivative of x squared, or 2x. And if we wanted to, we could go ahead and distribute this all out. So x to the 4th times 2x is 2x to the 5th. 5x squared times 2x is 10x to the 3rd. And then this will be negative 20x. Here's another example in the same vein. Pause the video, give it a shot. All right, so since we have the derivative of an integral, we're just going to replace the t in here with 4x. So we're going to have cosecant squared of 4x. But since 4x has a derivative other than 1, we're going to multiply by that tail of 4. So then 4 cosecant squared of 4x is our final answer. On this problem, we're trying to find big F prime of 2. So we need a derivative and then to plug in 2. Pause the video, try it out. All right, so let's take our derivative first. So I'm going to be doing x cubed to the 2/3 times my derivative of x cubed, which is going to be 3x squared. And let me just simplify this a little bit. So multiplying these exponents together, this is just going to be x to the second times this 3x squared is going to be 3x to the 4th. And then if I plug 2 into that, 3 times 2 to the 4th, that's 3 times 16, or 48. So hopefully you've got a good grasp of the fundamentals after this one. Till next time, Mr. Sutton signing off.